Okay, hi everyone. I'm Gabe. I'm one of the co-founders and CTO of Hatchet. I'm going to talk today about how to build production-ready AI agents. But just to clarify, after all the agent framework talk, we are not an agent framework. I'm going to talk about that at the end. But we are an orchestration platform where we'll get into some of the things that make us a bit unique and might help you guys as you're thinking through systems. A little bit more about me. So I helped build scalable agentic systems before it was cool. I've been doing a lot of things before it's cool. I don't think I'm cool yet, but maybe at some point I'll catch up. Basically, I've started my career in AI/ML, master's classical machine learning, and then I spent the last 10 years building startup systems, scaling engineering systems. I went through YC twice. My last was with a distributed remote video production company, which I'm going to talk a little bit about, and then most recently with Hatchet. So that video production company was an agentic system. It just didn't have any AI in the today's sense of LLMs. What we learned through this was basically scaling this video pipeline where we're able to deliver tens of thousands of assets, distributed humans all around the world taking videos, doing little discrete tasks, and then codifying all of what we've learned so far into a standard operating system, standard operating procedure, which was constrained. The key thing with humans and now LLMs and Daytona isolated compute, the humans break the constraints and give you a little bit of wiggle room to make the service actually work. And that's the whole thing when you're trying to scale something from a demo to production. You're going to have these edge cases. Things are going to start breaking. So we take this step-by-step thing. If people are familiar with DAGs, you can implement this as a DAG, or you can implement it as workflow as code. Hatchet supports both. But basically, we want to have consistent quality. We want to have consistent time for how things are executing. And we want to be able to measure each thing and use this agency to be able to make sure we actually can get the job done consistently. So we took all the learnings from building these agentic systems, and we started realizing about 2 years ago, LLMs are going to start replacing things, and the tooling is not really where it needs to be in order to make these large-scale production systems, so we built Hatchet. And we focused on low latency, Postgres, because everyone likes Postgres, and it's easy to manage and scale, and it provides durability, which I'll get to for statefulness. And we wanted to be code first with, thankfully, the 3 languages everyone in the room seems to know. So what I want to talk today a little bit more about are the 4 Ds of production-ready AI agents. These are what we've learned after the past 2 years. For the services that are most successful on Hatchet, that are LLM-driven, that use isolated compute, that codify these principles without, in a way that is constrained and scalable. So this is, I'm from New York. This is something that's a little bit different from every time we come to SF. All the demos, all the things people are talking about is how do we make these unconstrained services that do everything? In New York, we have insurance companies and really boring services where it's step-by-step and things have to get done correctly. And these are the 4 principles that we see most successfully being deployed into the thousands or billions or very large-scale kinds of services. So number 1 is distributed first. So if you're going to take a service that you want to be scaling in any kind of way, agents are becoming more asynchronous. They're becoming more data intensive. They're becoming more compute intensive. You need to be able to break down these individual components into small, scalable units of work that you can then deploy into different services. Just traditional computer science stuff, nothing engineering stuff, nothing crazy new. So we think the main primitive of agentic services should be a task, a thing that something needs to invoke. And tasks traditionally are just simple functions, and basically they make an LLM call, and as you start to scale, you can parallelize these tasks and break it down into smaller pieces and distribute the tasks. Nothing crazy, nothing new. With LLMs in particular, with these kinds of agentic services, you end up having resource constraints. So being able to take your distributed service and add rate limits and add concurrency keys and being able to shape that workload to match your constraints gives you that kind of benefit of being able to run as fast as you possibly can as you are scaling that service. The second thing that's important is building mostly deterministic services. So these tasks that you're designing should be constrained and predictable, right? So break them down to pure functions, simplicity, and if they are non-deterministic, try to take that edge case and constrain it as much as possible. So what we see, I think I'm missing a slide there, but what we see basically with isolated compute in this case is you will have a task that might have a tool, or rather the agent might try to call a tool that exists. If it doesn't exist, write a function, call that function, and basically try to constrain whether or not that was a successful invocation of the function. But it's not always the first thing that the agent will do. In the best systems, the best services, the code gen or the non-deterministic component is the fallback mechanism. And that's monitored, and basically as soon as you hit that case, you're starting to build for it if it's something that you're going to see more and more frequently. Another core principle we see work really, really well is build for durability. Is everyone familiar, or anyone familiar with durable execution? A couple. So this concept of durable execution is that you have your code maintains some kind of statefulness. So you have an orchestrator. We have all of our little tasks. Those are the things that need to be done, and there's an order by which those things have to be called. And then you have an orchestrator task, something that's the parent that's basically calling them in a specific order. In this example, basically, we have this hatchet.durable task. It's the same thing, except this is just an IO-bound, very simple function that is solely responsible for state. So if there's something that's long-running, for example, this image resizer, basically, this function can crash and be reassigned and pick up exactly where it left off, right? So when we're dealing with services that have isolated compute or these complex external compute requirements, building durable functions means that thing can break. It can fail. It doesn't matter because you can pick up where you left off and not have to pay for that expensive resource a second time. So as you start to scale these systems, cost becomes important, failure becomes important, and building for durable execution first gives you those kinds of guarantees and those kinds of benefits. Here's another example where Daytona has a great benefit where you can fork and create multiple parallel invocations, thousands of parallel invocations. You want to be able to maintain that state without having to think about that state. So if you basically create 1,000 plans, how do you orchestrate it? You have a durable function that's solely responsible for the plans themselves, put those plans into different tasks. Now those tasks are distributed, they are being run externally, and all of that state is basically saved without you having to think about where you're going to be storing it. And the last thing, I started to touch upon it a little bit, but basically you want these systems to be debuggable and observable. Basically, if you can't measure it, if you don't know what's working, then you're never going to be able to improve it. And as you start to scale these services, if you are solely responsible for this non-determinism, then you will start to see breakdown in the latency specifically, right? So you won't know how long things are going to be taking to deliver a certain service. You won't know if you need to be optimizing a certain component within your system because it's completely non-deterministic. So by breaking things down into basic first principles of how to design scalable distributed systems, you basically get debuggable and observable services out of the box. And yeah, to kind of round things out, do you need an agent framework? Probably not. So we've been deploying these services now for quite some time, and we've seen people start with agent frameworks and very slowly over months and months and months start to break down what they're actually using those frameworks for, and instead just encapsulating their own systems as they're hitting their own resource constraints, right? So I think isolated compute is actually a great example of this, where a lot of agent frameworks are not designed out of the box to handle these kinds of code gen use cases, and you start to realize you need to design your own encapsulation and your own constructs and paradigms for how you're actually going to be handling this sort of service. And by simply just designing things as tasks and your tool picker just picks the right task, you end up having the same kind of architecture with a lot more flexibility and freedom to choose the right tools and then solve the engineering problems as you eventually hit those constraints with those different tools. That's what I got. So I will be around after if you guys want to chat a little bit more about how orchestration, we see orchestration within the agentic workload space emerging. If you want to build with us, there's that QR code. We're open source and have a Discord if you guys want to hang out. And then if you do want to work with us, we have a few open roles that we are actively looking for. So thank you all so much.
Thank you, Gabe. Next up is Fred.